Okay, welcome back. We're going to get started with lesson 9.3. But before we do lesson 9.3, let's just quickly review certain things that we talked about involving square roots. For example, if we had, let's say, the square root of, let's say, the value of the number 9, that would give us a positive 3. If we had, let's say, the square root of, let's say, 100, and of course that would give us the positive number 10. We were working in chapter 9 involving a lot of things involving the radicals, and we even talked about cube roots, and we had said that if we had the cube root of, let's say, an 8, that would equal a positive 2. Because remember, we had the root index of 3, and we were asking ourselves, 2 to that power of 3 would give you that radicand, that number 8. Or remember, there's the little root index 2 that is understood here. And when we take the square root of 9, we're asking ourselves, what number that when I raise to the power of 2 would give us the radicand of 9? And of course, that's the answer here, 3. So now that we are familiar with these types of radicals, we have to ask ourselves, not everything will be a perfect square like, let's say, 9 and 100. Remember, I've given you a list of perfect square numbers back when we were dealing with factoring perfect squares. And let's just recall what those numbers were. Those were numbers like 1 and 4, 9, 16, 25, 36, 49, 64. Of course, there were more. Numbers like 81, 100, 121, 144, 169, 196, and 225. Those are all perfect square numbers, okay? And we used those numbers when we were dealing with the difference of two perfect squares, and they're going to become helpful once again with what we're going to be looking at in today's lesson. We also had perfect square variables, you may recall. Perfect square variables. And they were, some examples, x squared, x to the 4th, x to the 6th, x to the 8th power, x to the 10th, x to the 12th. These are all considered perfect square variables because the exponent, if we think about this algebraically, x to the n, okay, this would be considered a perfect square variable under the condition that n is an even number, which means it basically has to be divisible by 2. Okay, so these are all perfect square variable numbers, and these are all perfect square numbers. But let's say we want to take the square root of a non-perfect square number. For example, if we wanted to take the square root of the number 8, okay, now there is no number that when you square it, you get 8, okay, no rational number. So what we're going to have to do is we're going to use a property involving radicals, and that is a property of multiplication. And the property of multiplication tells us the following, that the square root of a times b equals the square root of a times the square root of b. So what this is basically telling us is that you can distribute a power, or in this particular case, you can distribute a radical, let's say, over multiplication. And we're going to use this property when we want to simplify the square root of 8, because that's what we're looking to do here. We want to simplify the square root of 8. So here's what we're going to do. One thing that we can do is we can take that square root of 8 and we can think of two factors. We want to come up with two numbers that multiply to 8. And we want one of the numbers to come from this list of perfect square numbers. So if we could think of two numbers, one of them coming from the list of perfect squares that multiply to 8, we could say that the square root of 8 equals the square root of 4 times 2, because 4 times 2 equals 8. Now, according to this property of multiplication, we can now distribute the radical over the multiplication, in which case now we would have the square root of 4 times the square root of 2. And since the square root of 4 is a perfect square, that would now give us 2 square root of 2. And this would now be considered your simplified radical. Just like we simplified fractions, we're always looking to simplify our radicals as well. Okay, so 2 square root of 2 would be considered your simplified radical. Let me show you another way of doing this. This is another approach that some students have liked as well. They think of the number 8 and they want to be able to write it as a product of prime numbers. So the number 8 can be brought down into 2 times 4. Now 2 is prime. However, 4 is not prime. We can break that up into 2 times 2 as well. So now, the square root of 8 is the same thing as the square root of 2 times 2 times 2, because 8 is 2 times 2 times 2. And so now what we're looking for is, since we are dealing with the square root, we are looking for a number, any number that happens 2 times, because that is the root index. Okay, so if we have a number under the radical that happens twice, I'm going to circle it. And by circling it once, that means we bring it outside the radical once. So now we're going to have a leftover 2 that's going to stay there. And we get the same solution as we did here, but just using a different approach. So once again, you can either take the number 8 and write it as a product of numbers. You want one of the numbers to be the largest perfect square possible. Okay? And so that's why we chose 4 times 2. And then we're able to use this property of multiplication, okay, that allows us to distribute a radical over multiplication. And now when we take the square root of 4, that just becomes the 2. And the leftover square root of 2 just comes along for the ride. So the 2 square root of 2, once again, is your simplified radical. Or we can use this second approach, that number 8. Once again, we use a little factor tree here, and we break it up into, first of all, 2 times 4. 2 is prime, so I put a little circle around it. And then the number 4 I break down, once again, 2 times 2. Those are both prime. So the square root of 8 is the same thing as the square root of 2 times 2 times 2. And since we are dealing with the root index of 2, we are looking for a number that happens twice. And if I have a number that happens twice, I circle it and I bring it outside once. Whatever is left over must stay under the radical. Let's do a different example. Let's say we want to simplify the square root of 24. Once again, I'm going to show you both methods. So the square root of 24, if we use the first method, I'm trying to come up with two numbers that multiply to 24. And I want the largest perfect square possible. So I'm going to use the factors of 4 times 6, because 4 is the largest perfect square number that goes into 24 evenly. Notice I didn't use 2 and 12, because neither 2 nor 12 are perfect square numbers. I didn't use 3 and 8, because neither 3 nor 8 are perfect square numbers. So I'm going to use the factors of 4 times 6, because 4 is a perfect square. And now I'm going to use this property of multiplication, and I'm going to distribute the radical and take now the square root of 4 times the square root of 6. And once again, the square root of 4, we know that is a perfect square, and that would give us 2 square root of 6. And that would be your simplified radical. Can't simplify it any further. What if we were to use that second approach? Let's take the number 24 and let's write it as a product of prime numbers, and let's see if I get the same solution. So when you think of 24, you might think of the first two numbers that come to mind might be 2 and 12. Now 2 is prime, so I'm not going to touch that. Let's take the number 24 now. 12 now. 12 has to be thought of as maybe 2 times 6. Okay. 2 is prime, but 6 is not. So let me factor down the number 6. And I'll once again use 2 and 3. 2 is prime, 3 is prime. So I can't break that up any further. So the square root of 24 is the same thing as the square root of 2 times 2 times 2 times 3. Now remember, we're looking for a number that happens twice, because that's the root index when we talk about square roots. And I have these two 2's that are being multiplied. So any number that happens twice, I bring it outside once. No other number is happening twice under the radical. So I'm going to have to take the 2 and multiply it with the 3, and that would leave us with a leftover square root of 6, which is the same answer that we have here. Okay? So that's just using a different approach to simplify the square root of 24. Let's try another example. Let's say we want to take the square root of 48. Okay. Once again, I'm going to show it to you both ways. First method, I need to come up with two numbers that multiply to 48. We want one of the numbers to be the largest perfect square that will go into 48 evenly. So I will use the factors of 16 and 3. 16 times 3 is 48, and the number 16 is the largest perfect square that is a factor of 48. And now I'm going to use that property of multiplication, which means I can now go and distribute the square root over the 16 and over the 3. And since the square root of 16, that's a perfect square, that gives us 4 with a leftover square root of 3. So 4 square root of 3 is your simplified version of the radical square root of 48. Well, if we were to use that alternative approach, let's see if we can come up with the factor tree for 48. And let's say we go with 48, and we want to break that up into 2 times 24. Well, 2 is prime, so I'm going to leave that alone. The number 24, let's break that up into two factors. You might use the factors 3 and 8. Well, 3 is prime, so we're going to leave that alone. The number 8, I'm going to break that up into 2 times 4. Well, 2 is prime, 4 is not. So I'm going to have to break up the number 4, and I will use the factors 2 and 2. They're both prime. So now, let's take the square root of 48 and write it as the product of prime numbers. Well, that would give me a 2 times 2 times 2 times 2, because there are 1, 2, 3, 4 2's there, times 3. Okay, so we wrote the square root of 48 as the product of these prime numbers. And now remember, since we are dealing with the square root, we are looking to find, do we have a number that happens twice? Well, here we have 2 2's, so that has to go outside once. Here we have another pair of 2's that must also get multiplied outside once. What remains under the radical is that square root of 3. And so now, since we have 2 times 2 on the outside, that would give us a 4 square root of 3 as your simplified radical, which is the same as the answer that we got up here. Okay? So you have to decide which method works best for you. You can either take the number and think of it just as 2 numbers, but one of the numbers must be a perfect square, the largest perfect square possible. Notice I didn't use 4, okay? Even though 4 is a perfect square, okay, that would not give me my simplified answer the quickest way, okay? So you could have also used this method where you take the number 48 and you write the number 48 as a product of prime numbers, and then you're looking for a number that happens according to the root index twice. So here we had a pair of 2's, here we had another pair of 2's. Each time you have a pair, it goes outside once. And then whatever gets multiplied together on the outside, and then anything that remains underneath the radical must also get multiplied together. I'm going to put up another example, and you should try it on your own. So I'm going to write down a problem, pause the video, try simplifying it yourself, and then start the video up again and see if you get the same answer that I did. So let's say we want to take the square root of the number 72. Okay, take a moment now, simplify that, pause the video, and either simplify it either way, okay, or maybe simplify it both ways and see if you get the same answer. So at this point, pause the video, work through the problem on yourself, and see if you can take the square root of 72 to get the simplified radical. And when you're done, turn the video back on. Well, now that you've tried that problem on your own, let's see what the correct answer is. If I was to do it the first method, the square root of 72, I'm going to try to think of 2 numbers. Okay? If I look at my list of perfect square numbers, I want the largest perfect square that will go into 72. And I know you might be thinking 9 times 8, because 9 times 8 does equal 72, and 9 is a perfect square. However, there is a larger perfect square that goes into 72, and that is the number 36. So let's go to that problem now. So the square root of 72 is equal to the square root of 36 times 2. And now we could use that property of multiplication, and I can now distribute that square root of 36 times the square root of 2. And the square root of 36, that's a nice perfect square. That would just give us 6, and the square root of 2 comes along for the ride. So our simplified radical is 6 square root of 2. Well, let's see if we use that second approach if we get the same exact solution. So I need to come up with two numbers, any two numbers that multiply to 72. Well, what if the first two numbers that come to mind might, let's say, be 9 and 8? Okay. Neither 9 nor 8 are perfect squares. So, I'm sorry, 9 or 8 are not prime. So I'm going to have to take the number 9 and I'm going to write it as 3 times 3. Well, 3 is prime and 3 is prime. So I don't have to do anything there. The number 8, however, I'm going to break that up into 2 times 4. 2 is prime, but 4 is not. So now let's take the number 4 and break that up into 2 times 2. These are both prime. I don't have to go any further. So now I'm going to take the square root of 72 and I'm going to write it as the product of, let's say, 3 times 3 times 2 times 2 times 2. If I was to multiply all these prime numbers back together, it would bring me back to 72. So now let's see what we can do. We are looking for pairs of the same number because we're dealing with square roots. So here I have two 3's. They go outside the radical once. Here I have a pair of 2's. So they must also go outside the radical once. And what remains is just this 1, 2. So now let's take that leftover 2 and leave it under the radical. We don't leave our answer like this because we could actually perform this multiplication, and 3 times 2 is a 6 square root of 2, which gives us the same answer that we did up here. So hopefully you're beginning to develop a better way, or let's say a better understanding of which method you feel works best for you. Because in the end, you're going to get the same solution. Whether you just do it with two numbers, or whether you are more comfortable coming up with a list of prime numbers that multiply to the original radicand, in the end, you get the same answer. Let's try another problem. Let's say, for example, you want to simplify the square root of 75. Once again, pause the video at this point and try either method or both methods, whatever you prefer, and see if you can come up with the simplified radical for the square root of 75. So pause the video. Now that you're back, hopefully you were able to work through this, and let's see if you got the correct answer. Once again, I will use the first approach. I need to come up with two numbers, one of them being a perfect square, and the largest perfect square that goes into 75, I'm going to use the factors of 25 times 3. Since 25 is a perfect square and 25 times 3 equals 75, we're good to go. And so now I'm going to use that property of multiplication, and I will take now the square root of 25 as well as the square root of 3. And the square root of 25, that's a perfect square. So now that would give us just 5 square root of 3. And that would be your simplified radical. If we were to do the same thing now and use that second approach, let's take the square root of 75 and write it as maybe, let's say I was to do 3 times 15, because 3 times 15 is 75. And 3 is prime. Now we need to break up. Wait a second. I stand corrected here. I don't want to do 3 times 15. I want to do 3 times 25. Okay. 3 times 25 is 75. And if we want to now break up 25 into 5 times 5. So now let's write the square root of 75 as 3 times 5 times 5. And once again, since we are looking for 2 numbers under the radical, we have this pair of 5s. That means that goes outside once, and what's left over is just the square root of 3. And once again, we get the same simplified answer as we did earlier. So that's how we simplify square roots that contain non-perfect squares. Okay. Now, numbers can't have all the fun. We can also take the square root of variables. And so if we take the square root of, let's say, x squared, we get x. If we were to take the square root of, let's say, x to the 4th, we would get x squared. If we were to take the square root of x to the 6th, that would give us x cubed. If we were to take the square root of x to the 8th, that would give us x to the 4th. Now, how are we getting these solutions? Well, remember, since we are dealing with the square root as our understood root index, basically all you have to do is that you are taking the exponent that you see here and you have to divide by the root index, because 2 divided by 2 is 1. There is no remainder. So that's why there is 1x on the outside. For the second example here, now I'm going to take the exponent of 4 and divide it by the root index of 2, and that goes twice with no remainder. And that's why there is an x squared left over. Okay, this number that you see here is representing the exponent of the variable. So, once again, if we take 6, that's the exponent, and we want to divide it by the root index. Well, 6 divided by 2 goes 3 times evenly with no remainder. And that means we're going to have x to the 3rd power as our solution. And even over here, the square root of x to the 8th. We take the exponent of 8, we divide it by the root index of 2, and that goes evenly 4 times, no remainder. And that's why we get x to the 4th power as our simplified radical. So even if we were to do a more difficult, a higher power, let's say we were to take the square root of x to the 24th power. Well, let's see what that's going to give us. If we take 24 and divide it by, remember the root index is 2. 24 divided by 2, as we see here, that gives us a 12, remainder 0. So that means we're going to have an x to the 12th power on the outside. And once again, you'll notice that there is no radical left over, okay, because x to the 2nd, x to the 4th, 6th, 8th, and 24th powers, these were all perfect square variables because your exponent here is an even number. Even if I was to include numbers and variables, let's say we were to take the square root of 36, x to, let's say, the 40th power. Well, what we can do is take the square root of 36, and we can take the square root of x to the 40th separately, because just like we were able to use that distribution property of the radical, that property of multiplication, we can distribute this radical on the number as well as on the variable. Well, If we were to take the square root of 36, that's just 6, because 36, remember, is a perfect square. If we were to take the square root of x to the 40th power, well, like we did up here, we need to, of course, now take the 40. We're going to divide it by the root index, which is the understood 2. 40 divided by 2 is 20, no remainder. So our solution, we have to take the solution to the square root of 36, which is 6, and we have to take this solution, which would give us x to the 20th, and that would be your simplified radical. Let's do another one. Let's take the square root of, let's say, 49 x to the 50th y to, let's say, the 62nd power. Well, once again, let's split this up into the square root of 49 times the square root of x to the 50th times the square root of y to the 62nd power. We can do that because of that property of multiplication. And so now, we're going to take the square root of 49. That gives us 7. And then we have to take the square root of x to the 50th. Remember, we take the exponent, we're going to divide that by 2, the root index, and that goes evenly 25 times, no remainder. So this would become x to the 25th power. And if we were to do the same thing now with the square root of y to the 62nd, we're going to take that 62nd power, we're going to have to divide by the root index of 2. 62 divided by 2, that goes 31 times, no remainder. So now we're going to have a y to the 31st power. So now I have to take my 3 separate solutions, and since they're all being multiplied up here, we would have to multiply them for the final answer, giving us a 7 x to the 25th y to the 31st power. Let me give you one to try. Let's take the square root of, let's say, the number 81, x to the 20th, y to the 32nd power. Pause the video at this point and try the problem on your own, and then when you're done, check back on and see how you did. Well, if we were to break this up using that distribution property, the square root of 81 times the square root of x to the 20th times the square root of y to the 32nd power. Now let's go and do each one individually. Well, the square root of 81, that's just 9. When we take the square root of x to the 20th, remember, we take the exponent, we have to divide by the root index 2. 20 divided by 2 would give us a 10, remainder 0. So that means we would have an x to the 10th power as our answer. Now when we go and we take the square root of y to the 32nd power, we have to take 32 divided by the root index 2, and that would give us 16, remainder 0. So that means we're going to have a y to the 16th power as our simplified radical. We now have to go and take our 3 solutions and just multiply them together, and we would get a 9 x to the 10th y to the 16th as our simplified radical. Now, Those were all nice problems because they were all dealing with perfect squares. So what if we were dealing with the square root, not of x to a even number, but maybe of x to the 9th power? Now, this is not a perfect square variable because 9 is not an even number, and we want to simplify this. So, just like we did with these exponents, we have to take the exponent of 9, and we're still going to divide by the understood root index of 2. Well, 9 divided by 2 goes 3 times, but there is a remainder of 1 left over. I'm sorry. 9 divided by 2 goes 4 times, remainder 1. Okay, so what does that mean? That means we're going to have an x to the 4th power, and there's going to be a leftover x to the 1st power under the radical. So these numbers here give me the exponents of the quantity that's outside as well as the quantity that is underneath the radical. Let's do another problem. Let's take the square root of, let's say, x to the 15th power. Now once again, x to the 15th power is not a perfect square variable. So I'm going to take the 15, the exponent, and I'm going to divide it by the root index square root of 2 here. And since 15 divided by 2 goes 7 times, remainder 1, okay, that means we're going to have an x to the 7th power and a leftover square root of x under the radical. Okay, because this 7 is the exponent here, and the 1 is the understood exponent here. And this would be your simplified answer. Let's try another. Let's take the square root of, let's say, maybe x to the 25th power. Okay. Don't be alarmed by the 25 being a perfect square number. Now the number here, 25, is acting as an exponent. So once again, we're going to have to take that exponent of 25 and we're going to divide it by our, once again, root index. The index is understood to be 2. 25 divided by 2 goes 12 times with a remainder of 1. So that means our simplified radical of the square root of x to the 25th would give us now x to the 12th power and a leftover square root of x to the 1st power. Okay? What goes in evenly becomes the exponent of the outside variable. Whatever that remainder might be becomes the exponent of the variable that still hangs out under the radical. Let's try one a little bit more complicated. Let's take the square root of 20 x, let's say, to the 19th power. Well, the first thing that we're going to have to do is split this up into the square root of 20 and the square root of x to the 19th power. And now let's go and take the square root of 20 first. And the square root of 20, I need to come up with two numbers, one of them being a perfect square. So I'll use the square root of 4 times 5. And now we would break this up into the square root of 4, square root of 5. And the square root of 4, that's a perfect square, giving us a 2 square root of 5. So this would be your simplified first part. Okay. Even if you used the second approach, oops, sorry about that. The second approach, remember, would be to take 20 and write it as the product of prime numbers. And that would be 2 times 2 times 5. And since we have a pair of 2's, that's how we would still get 2 square root of 5 as your simplified radical. So use whichever method you prefer. Now, once again, remember we have to take the square root of x to the 19th. So 19 gets divided by the root index of 2. 19 divided by 2 goes 9 times, remainder 1. So now we're going to have an x to the 9th and a leftover x to the 1st, and that would be your simplified radical. So if we combine these two, remember anything that's outside the 2 and the x to the 9th have to get multiplied together. So we're going to have a 2x to the 9th, and then what's underneath the radical, which is the 5 and the x, we're also going to multiply together. So that would give me the square root of 5x. And that would be your simplified radical. Let's try another. Let's take the square root of, let's say, 12 x to the, let's say, 11th power times y to the 21st power. Well, first thing that we would have to do is break this up into the square root of 12, the square root of x to the 11th, and the square root of y to the 21st. Okay, it's that distribution property that allows us to do that. And so now, I'm going to go and simplify each radical independently. So let's start with the square root of 12. And the square root of 12, I'm going to write that as the square root of 4 times 3. Because 4 is a perfect square number, and 4 times 3 is 12. And so now that would give us the square root of 4 times the square root of 3. And when we take the square root of 4, we just get 2 square root of 3. So that would be the simplified version of the first part. Now let's go and take the square root of x to the 11th power. Remember, we take the exponent of 11, divide it by the root index 2. 11 divided by 2 goes, oops, jumped again. 11 divided by 2 goes 5 times, but there is a remainder of 1. So that's how we would get x to the 5th and a leftover square root of x to the 1st. That would be the simplified part 2. We have to now do the square root of y to the 21st. Well, once again, we're going to take the exponent of 21. We're going to divide that by the root index of 2. 21 divided by 2 goes 10 times. Once again, remainder 1. So this would become, in terms of our simplified answer, a y to the 10th and a leftover square root of y to the 1st as your simplified radical for y to the 21st. Once again, to come up with your final answer, you're going to take the 2, the x to the 5th, and the y to the 10th, and we're going to bring them all together. So we have 2 x to the 5th, y to the 10th, outside, and anything that's still hanging out under the radical we will also bring together, giving us now the square root of a 3xy. That is your simplified answer to that particular problem. Let me give you one now to try. Okay, once again, I'm going to put up a problem, pause the video. When you're done, come back and let's see how you did. Let's say, for example, take now the square root of, let's say, 40 x to the 7th y to the, let's say 13th power. Pause the video, work through the problem, and when you're done, turn the video back on and let's see what you got for your answer. If we were to break this up into the square root of 40, square root of x to the 7th, and the square root of y to the 13th. Once again, now let's form three different radicals. The square root of 40. When we were simplifying that, we might use, let's say, the square root of 4 times 10, and that would now give us the square root of 4 times the square root of 10. And since the square root of 4 is a perfect square, that would give us a 2 square root of 10. That would be your simplified radical. Now let's do the square root of x to the 7th. Well, we have to take the exponent of 7, and we're going to divide by the root index 2. 7 divided by 2 goes 3 times, remainder 1. And so now our answer to that part would be x to the 3rd square root of x to the 1st. And that would be your simplified radical for the second part. For our third part, we are taking the square root of y to the 13th power. And so now we take the 13 exponent, divide by the root index 2. 13 divided by 2 gives us a 6, remainder 1. And so our solution to that third part would become a y to the 6th and a leftover square root of y to the 1st. So now you're going to take your three solutions. Anything that's under the radical, which is the 2, the x to the 3rd, the y to the 6th, we bring together. And anything that's still hanging out under the radical, which of course is the square root of the 10xy, we just multiply back together. And that would be your answer to that particular problem. Okay, so we had a property that allowed us to distribute a radical over multiplication. Okay, we had a property of multiplication. Once again, that told us that we could take the square root of a times b equals the square root of a times the square root of b, because you can distribute a radical over multiplication. Well, believe it or not, and I got no reason to lie to you, we also have a similar property when it comes to division. The property of division tells us that the square root of a over b equals the square root of a divided by the square root of b. And I'm going to suggest that if possible, okay, you want to simplify the fraction first. So if possible, you want to simplify the fraction first. So you want to look at your fraction of a over b, and if you can simplify that, please do so. It might make the problem easier for you. So for example, if we have the square root of 36/25, okay, well, let's take a look at this fraction. Can I simplify? Is there a number that goes into 36 and 25 evenly? The answer is no. So we can't simplify this fraction. So now what we can do is we can use this property of division, and we can distribute the radical on the numerator, square root of 36, and on the denominator, square root of 25. And now let's go and take the square root of each one. Well, the square root of 36, that's just 6. And the square root of 25, that is the number 5. So the square root of 36/25 is the same thing as 6/5. Let's try another. Let's take the square root of, let's say, 2/8. Well, once again, if possible, you want to simplify the fraction first. So let's ask ourselves, can we simplify the fraction 2/8? And sure enough, we can. Since both numbers are divisible by 2, the square root of 2/8 is the same thing as the square root of 1/4. So now that we simplified our radical, now let's go and use the property of division. And now let's take the square root of the top, 1, as well as the square root of the bottom, the denominator 4. And since the square root of 1, that equals 1. And the square root of 4, that's 2. So the square root of 2/8 becomes 1/2. Of course, we can also do it with variables. Let's take the square root of, let's say, x to the 4th over y to the 10th. Well, we can't simplify this fraction, okay? And so now we would take the square root of the numerator, x to the 4th, over the square root of the denominator, y to the 10th. And, well, since 4 is a perfect square, we can divide 4 by 2, and that would give us x squared on top. And if we were to take the 10 and divide it by the root index 2, 10 divided by 2 would give us y to the 5th in the bottom. And that would be your simplified radical. Let me give you one to try. Go and take, let's say, the square root of 49 over x to the 20th. Pause the video and try that one. Well, since we can't simplify our fraction here, we're going to go and take the square root of the numerator over the square root of the denominator. And the square root of 49, that's a nice perfect square. That would give us 7. And the square root of x to the 20th, that too is also a perfect square because 20 divided by 2 would give us just x to the 10th. And that would be your simplified radical. Okay. So that is section 9.3. Okay. There is, of course, some homework problems from the textbook that coincide with this. You should give those a try. And if you have questions about things, shoot me an email and I will, tell me what problem you are having difficulty with, and I will try to work through an explanation for you and then email you back an explanation. Okay?